All right, folks, so we spent some time going over conventions in MIPS. Time to put rubber to the road and actually convert some C into some MIPS. So what we've got here is an insertion sort program. All it's going to do is walk through the array and shuffle items to the left if they're too big for their current position in the array. To do that, we've got this helper function swap, and let's actually have that be the first thing that we go ahead and write, because that is going to be substantially easier to write the MIPS code for than the actual insertion sort. So the first thing we're going to want to do is we need to have a label so that we can actually call this function. Swap seems like a good thing to call it. And then we're going to have A0 is going to be our array. A1 is going to be I1. And A2 is going to be I3, or I2. Yes. So the reason we did that is just R is our first argument, I1 is our second, I2 is our third. So that's sort of the convention for converting what arguments a C function receives to what registers they will be in when you call MIPS. So with that in mind, we are going to be using I2 and I1 as offsets into arrays. So the first thing we want to do is we want to scale those up for a pointer arithmetic, and that's going to be a multiplication by 4 for both of them. And we do that using an SLL by 2, which will just slam 2 zeros onto the right-hand side of our number here. Do that for A2 as well. And now we have some legitimate addresses. Now let's calculate the value that we're actually going to address. So we have our offsets. We add it to the base address to get what we actually offset. So going to store into A1 R plus I1. And to do that, we just use an addo. Into A1, R we had was in A0, and I1 was previously in A1. Now, of course, we've clobbered that, but we're not going to need I1 anymore in the function, so that's okay. Similarly, for A2, we go ahead, add that on to A0, and now we can actually use these as addresses. So let's go ahead and grab the values at those addresses, and it's about time we started using a T register here. As a reminder, we don't care what we do to T registers. The function that called us does not expect those to be preserved, unlike S registers, which you'll notice we didn't have a prologue on this. So if we do wind up using any S registers, we're going to need to go ahead and add a prologue on retroactively. So anyways, what we've done here is made an error. This needs to be a separate register, but T1 is going to be receiving R at I2, and T0 received R at I1. And now all we have to do is go ahead and finish up our swap by storing in reverse order. And we're going to store instead of into A1 and then A2, into A2 and then A1. And hopefully it's clear that that will swap the values. And then the last thing you have to do for any function call is jump register RA, which will take us back to where we came from. All right, so that is our swap function. So we can now call that safely when we write our insertion sort. And our insertion sort has a number of variables that we're going to want to keep track of throughout our time writing it. So I'm going to use our S registers to do that. So I is going to, throughout our execution, correspond to S0. J is going to be put in S1, and I will be keeping R and size in S2, and in S3. R and size will initially be passed in to A0 and A1, but as we noted in the first exercise, those values are not guaranteed to be preserved, so when we call swap, they could disappear. And in fact, as we see, we did clobber A1 and A2 in our call to swap. So now the first thing we are going to need to do in our insertion sort, 1, give it a label. 2, we're going to need, because we are using these S registers up here, we're going to need to have a prologue. So let's give ourselves a stack frame. And to do that, we're just going to move the stack pointer down by some amount. I'm going to leave that blank for the time being because I'll need to figure out what variables exactly I'm going to need to save. So just so that we don't have to keep scrolling back to look at this, I is in S0, J is in S1, R is in S2, and size is going to be in S3. So just have that off in the corner there for reference. So we've used 4 S registers, so we're going to need to save those certainly. So that'll be 4 store words to save those values. And that's just going to be store S0, S1, S2, S3, 0, 4, 8, 12. Notice that I'm counting up by 4 each time because I am storing words, which in MIPS are 32 bits, 4 bytes, and everything these days is going to be byte addressed. And that is all going to be stored off of the stack pointer. Alright, so we also know that we're going to need to save RA because we're going to call jump and link to get into swap. So that's another thing we're going to need. And then it's going to turn out that we're going to want, actually, no, we're not going to need any others. Looking at my code over there that I already wrote. So if you're wondering how I know to do all this, I'm cheating. But we'll notice we're storing 5 elements on there. So each one needed 4 bytes of space. 5 times 4 is 20, so we move the stack pointer down 20. Remember, the stack grows down in memory. So now we've got our prologue in. Let's start writing code. And the first thing we want to do is I said S2 was going to be R, and I said size was going to be in S3. So let's actually make that the case. So A0 would have been passed in place of R, and size is going to get passed in inside of A1. So we'll just move those into S2 and S3. And now we have saved our argument registers and can start initializing things. So at the top of our code, we see here we have a for I equals 1. Step 1 in that for loop, let's initialize I to be 1. A little bit of technical difficulty there. So add a U into I is going to be in S0. Zero plus 1 had better give us 1. So this is our I equals 0 initialization. All right. Then we can get into the actual for loop, which I'm going to give the label for loop. If you're writing MIPS and there are a whole bunch of other functions around, for loop is maybe a little bit too general of a name because there can only be one label with a given name in each MIPS program, but for our purposes it's fine here. And we'll notice our condition for continuing into this for loop is that I is less than size. So I'm going to run that comparison here and do SLT, store into T0, whether I is less than size. I is in S0, size is in S3. And just to keep track of all of this, we're going to keep a whole ton of comments going, because what you'll learn as you're coding MIPS is it's a lot harder to read than, say, C or Java, and comments are really the best way to keep track of what everything means. So T0 is going to be holding whether, whether or not I is less than size. All right, and then I'm going to say if I is not less than size, that is if T0 is equal to 0, then branch to the end of the for loop. We haven't written a for loop end label yet. We'll figure out where to put that once we've finished writing our for loop. With that, we can actually get inside of our for loop. And the first thing we do is we assign j equal to j equal to I. So to do that, it's just a simple move. Move is a pseudo instruction. So if you were actually writing true MIPS code, you would have to use, ADDU, destination, source, and a 0. But for legibility, we're going to use the pseudo instructions here. So we're going to be adding into S0, S1, S0, and then that plus 0, which gives us that move instruction. So this is j equals I. All right. Next, we're going to hit that while loop. So we're going to want a label for that loop. And the while loop has conditions for running, which are j greater than 0 and rj less than rj minus 1. So how we're going to encode this is we're going to check if j is greater than 0, and if it's not, we're going to break. And then after that, we're going to check if rj is less than rj minus 1. And if that's not true, we're going to break. And then only after both of those are true will we perform our swap and decrement. So j greater than 0, we don't have a set on greater than comparator. So we're going to have to do just a little bit of arithmetic to figure out what that means. What we want is j greater than 0 is obviously the same thing as 0 less than j. So we're going to do an SLT. Going to use T0 again because I don't really care at this point what was in it before. That comparison of I less than size has already served its purpose. So we're going to store into T0 here whether 0, so our 0 register, is less than j, which is stored in S1. And if that comes out to be true, then we're going to keep following through. So another way of saying that, again, sometimes it helps to write the comment before you actually write the line of code. So we're done if not 0 less than j. So we're going to branch equal T0, 0, and then we're going to have another place for our while loop to end, which I will call while loop end. All right, so that is our first check. Our second check, we have to look into memory. And to do that, we're going to have to first take j and scale it by 4 so that we can use it as an offset to a memory address. We have here rj. So as a reminder, ints 4 bytes. And this is a really easy thing to forget. I forget all the time that I need this SLL into something you know, T0 is just our scratch space right now, but you need to do this SLL S12 thing to get that multiplication by 4. You can't just add it in directly. And what we've done thus far, we just went ahead and now T0 holds J times 4, and we need to do that multiplication by 4, of course, because while C does it implicitly, MIPS is all quite explicit. All right, so we've done that, and now let's actually get an address out of it. So T1 will be R, which should be in S2. So we add S2 to T0, and in doing, we get R plus J in C, which, if you prefer to think of it this way, address of R at J. Both are equivalent. Personally, I prefer the one on the left because it's a little bit more succinct. All right, so now we've done that addo, let's do some loads. So I'm going to load into T0 since I've already done my address calculation. I don't need to keep this J times 4 around anymore. So load off of R ampersand R at J. And in that way, T0 now has R at J. All right. And now I'm going to load into T1, because after this load, I'm not going to care about that address I calculated. Minus 4, because I want R at J minus 1. So we drop it backwards by 4. And T1 is the address we calculated. So this will give us T1 gets R plus J minus 1 star, just using different notation here to make sure everybody gets exposed to all of it. We've done our loads. Now it's time to do a comparison. So after this comparison, I'm not going to care about what's in R at J, so I can clobber that. And I'm going to compare T0 to T1. What is that doing? Well, that's saying T0 gets the value Rj less than Rj minus 1. All right, so if that's the case, let's go back up to our C code for a moment. If Rj is less than Rj minus 1, we're going to want to keep going. So if that's not the case, we're going to break. So if we have put a false, which is 0, if we put a 0 into this T0 here, we're done. So that's once again going to be BEQ T0, 0, and this will be finishing our while loop. All right, so now we've done our branch checking, or our loop checks rather, and we can move on and start doing the actual contents of that while loop. So inside the while loop, we just had two C lines, swap R, J, J minus 1, and J minus minus. So for the first one, we're going to need to put into a 0 the value of R, which we have saved in S2. So that's A0 gets R. Similarly, we're going to need to move into A1 the value of J, which is hanging out in S1. So A1 gets J. And then we can't use a move for this next one because we need to decrement by 1. So this next one, what we're going to do is we're going to say, all right, just use an actual ADDU, no pseudo instruction here, and into A2, S1 minus 1, and thus A2 as j minus 1. All right, we are now ready to call swap, which is as easy as JAL swap. All right, so three lines of prep and then one line to actually call the function. After that returns, all of our S registers are safe, but we can no longer trust anything in any of our T, A, or V registers. Well, I guess we can trust things in our V register if we know what's supposed to be returned. Although swap has no return value, so we can't trust it. All right, we've called swap. What do we do next? We have to decrement J. So that's just going to be add U. Instead of putting it into A2, we're going to put it into S1. So basically the same as our line, just 2 up. So this is J equals J minus 1. All right. Now we're at the bottom of our loop, and we go back to the top of our while loop. The reason we do this right at the end here is because that's how it works. But a very common sort of paradigm for doing while loops is you sort of have a, in MIPS, check if stop, and then if you do, go to the end, else at the end, jump to loop. So our sort of control flow is like this. We'll check if stop, and if we do stop, we slide ourselves in right after this J loop, and if we don't, at the bottom of our loop, we'll automatically go up to the check if stop. All right, so we've now finished our while loop, with the exception of one thing. We need this check if stop to have somewhere to jump to. If you recall, we called that while loop end. So we're going to place that right after that J. Okay, so after the while loop ends, it looks like we don't have anything more to do in this for loop, and we would just put for loop end there. But remember, we have to increment our counter. So we go ahead and we do that. I is living in S0. So add EU, S0, S0, 1, and I++. All right, so we've done that. And now we can say jump for loop, because we finished the logic in our for loop. And the last thing we have to do is say for loop end, so that when we realize that I is larger than or equal to size, we can get the heck out of there and not keep doing things we're not supposed to do. Okay, so that is most of the logic. We just have one last thing to do, and that is we're going to need to have an epilogue. So at the very top here, if you recall, we went ahead and we saved all these values onto the stack, S0, S1, S2, S3, and RA. We saved RA because we're going to clobber that ourselves, and we need to be able to get back to whoever called us. And we saved S0 through S3 because we clobbered those, but whoever called us expects those to be the same when we get back. So we better restore them before we return. So let's go ahead and do that. That's going to be as simple as a series of load words. So load word, we had 5 values, so that's going to be 5 load words. And we are going to need, it's important that you pull them out of the same place you put them into. Hopefully that's obvious. So our order was S0 through S3 and then RA. And of course, the actual order of the loads doesn't matter. But it's very convenient to keep them in the same order so that you can do what I'm doing right here and just write them all at once. So it's going to go 0, 4, 8, 12, 16. I don't even have to think about it. It's just next one, next one, next one, next one, and it's all going to be where it needs to be. We saved these in our stack, so we're going to pull them off of the stack. All right, we've restored all our variables, And we have just one last thing to do. Jump register, RA, and now we go back to whoever called us. And that's it. Okay, so hopefully all of you are acting all manner of angry and confused because I've done something terrible here. And that is, right in here, we need to move the stack back up to where it was before we were called. So that's bad. What we want to do here is pop the stack. So we're going to add on 20 to the stack because we subtracted 20 to move it when we pushed all our values onto it. And after that, we can actually return. Now let's do some analysis of MIPS conventions. So why did we save registers to the stack in our code? We discussed this. Whoever called us, our S registers need to be preserved. There's no like hardware enforcing this or anything, but if you're not doing this, basically you're a terrible person. Whoever called you, you're going to ruin their day. So, you know, don't be clobbering S registers if you're not going to put them back the way you found them. And then the other thing, our RA register, we clobbered it, but we need to know how to get home. So we need to save that. Otherwise, we're going to be in even more trouble than if we ruin somebody else's day. So how did JAL and JR make our lives easy? Well, basically, if we didn't have JAL and JR, we would have had to hard code our jump registers at the end, and we could only be called from one place. So made it possible to be called from multiple places. Now, if we didn't have these instructions, we could still, in principle, have these be callable from multiple places. But each time you called them, you need to copy the code and hard code in a different jump return location. So that would be terrible. Your code would blow up in size, and it would be incredibly inelegant. So why are we branching and looping? Or rather, what is the difference between branching and looping in the loop and jumping for a function call? So the difference is really if you're in a function call, you're going to use JAL and JR, and that allows you to sort of dynamically determine where you should be jumping to. Whereas a loop, you're just going to use, jump, BNE, BEQ, whatever, and that's just going to have you, run in a loop. These are a little bit obvious. It's something you've seen all the time in C, the difference between a function and a loop. And here we're just seeing that assembly code has slightly different constructs for supporting both of those. All right, now we're actually done.